Someone also asked to go back to slide 9 for a second.
We are on slide 9.
Oh, not 9. I mean 8. Sorry.
Okay.
Oh, I guess the.
Yeah, it erases it. It'll be on the. It'll be on the end of the video that I'll post tomorrow.
All right.
Okay. So the snake thing, we decided for the term that we had, it was 1.2. How is that going to affect the real function? If I do an exact plot of this using something like MATLAB, if I have the snake affects something called gain peaking. And you can see here that I get controls people use this. I can vary the value of that snake, and I can get varying levels of gain peaking right at omega naught, or I can have gain damping at omega naught. And it has kind of a similar effect on that. For the lab, we generally just ignore it. And when we do a notch filter in the lab, we'll kind of use this effect to create a really steep notch by having a bunch of attenuation just right at the omega naught. I'll explain that when we get to it in lab. I will be there. I don't have to do everything in class anymore. Okay. If I have a quadratic pole, it's amazingly similar, except for the graphs look like they weren't written in another alphabet. It is same form. When we put it in this form, the only number we really need to pick off is once we get it in this form is what is omega naught? And I always call it omega naught because that's the way I think. That's the way engineering, yeah, okay. The straight line approximation looks like it's 0 until I get to omega naught, and then it falls by 40 dB per decade. Same thing with the phase shift. Now instead of going down 90, it's going down 180 degrees, still taking 2 decades. And I get the gain peaking if there's a snake. And you can tune that to get, sometimes you want a lot of gain right at omega naught. Sometimes you want to attenuate the gain even more at omega naught. You can play with that and get what you want. And that is a topic that the only place you'll see this in a modern engineering curriculum anymore is if you're in controls theory, which is a close cousin to power system engineering. So anybody who's wanting to do alternative power or work for the power company, the exciting work working for the power company right now is not the 60 hertz grids stuff that I slept through when I was in college. It's more fun now because they have like these DC to DC converters and DC to AC converters to be able to hook a wind turbine, a solar power panel up to the grid and make sure everything's locked on 60 hertz in phase and not disrupting your grid. So there's a lot of controls theory involved in that. You'll see more of this in Dr. Yaramasu's classes. And maybe Dr. S will teach a controls class for us soon. It's somebody else's work to write the class, so I don't mind. So yeah, it's basically the same thing. Now we went over that one. Now this is why we're doing this. We've gone through and all we've done is done Bode plots of individual factors. In the real world, you're mostly doing Bode plots of or frequency response curves of single there's like a single pole or 0 or things like that when you're looking at it and trying to estimate it. But when you get these more complex functions, okay, remember, we are always plotting, all these things I'm plotting, it was a magnitude in dB. And dB equals 20 times the log of something. And 20 times the log, this is the magic of slide rules, 20 times the log of 2 things multiplied together is the same thing as 20 times the log of 3 plus the log of 10. So if I have two things multiplied together, I can find the log of each one of those things that were multiplied together and add the results together, and it's just like multiplying. If I have a transfer function that has put it in right form. Something, oh, wait, that's not quite right form. That looks something like this. What I could do is I can find the Bode plots of each one of these factors and add them together instead of multiplying them. I can add them together graphically fairly easily.
So that's the factors on the top, right, in the numerator?
Yeah, there's factors in both in the numerator and the denominator. The ones in the denominator I'd have to subtract, well, I'd have to, they're just going to be negative because poles fall. That's why poles are negative.
Oh, okay, all right.
Well, we're
So
going
you
to go,
combine the,
yeah.
do you combine the plots of the poles on the in the numerator as well as the poles in the denominator and just add them together into a
Yes.
single plot?
I find the Bode plot of each one of the factors and I add them together. But I have to add them together across frequencies. We'll do this in bamboo paper really quickly. Now for phase shifts, remember when you were multiplying things in polar form back in 188, what you did is you multiplied the magnitudes together and you added the phase shifts. So the phase of this thing would just be 25 minus 40, which is negative 15. So if I have something that's a phase shift, and it's a one phase shift multiplied by another phase shift, each one of these factors has a phase shift, and I multiply them together, all I have to do is add the phase shifts. That's what we're going to be doing next. Looking at real pseudo transfer functions and figuring out what the Bode plots are. So this is my divide and conquer strategy. This is my own slide, and so just forgive me. I've got a really complicated transfer function, 40s times s plus 1, and I put it in standard form this semester. 1 plus s over 10 squared, 1 plus s over 3 squared. This one isn't standard form, but I'd have to do that to get this right. You have to put it in standard form first. The way I would do this is 40 is a constant. So I go back to, all right, I've got it memorized now, but you could go back to that little note sheet and say, how do I plot a constant? And plot the graph of that. S by itself is a 0 at the origin. I go back to that little note sheet and I figure out how to plot that graph. And I do that for each one of these terms. And I find their Bode plots. I add the magnitude and phases together, and I have the Bode plot of the whole function without having to multiply that out. You can do this on a piece of paper. You can do this on the back of an envelope. You can almost, when they're simple enough, you can almost do them in your head. And if you're an engineer who's working in anything like data acquisition, controls theory, power systems, anything analog, within a year or two, you'll start doing simple things like this in your head. It takes a little while to get there. The ones we look at in 380 are much easier than in here, but I threw circuits on top of it. So let's just do an example. And this is why I had my bamboo paper open. We're gonna go here. Knock a few times and hopefully it opens. Oh yay, there we go. Did it go back? Yes, it went back to where I was going. Okay, so I'm gonna move this thing out of the way. So this was the example we're looking at. If we look at this, what we have here, we have a constant term, and my pole is already in standard form. So what I have here, I don't have to mess around with it anymore. My K equals 30, and I have a pole at 10's already in the denominator. I have a pole, simple pole, at omega equals 10. Okay, so we're going to do this. I can write much neater on bamboo paper. So this is why I transferred this over. I did that with my finger though. K equals 30. We're going to draw the magnitude plot of that. And label these. I give you graph paper on the exam, but I don't label them for you. So this is AV. I do everything AV. Magnitude of AV, the units are decibels. I'm going to need, it's a pole, poles fall. So I'm going to put 0 here. I'll put like minus 20 here, and that's in dB because I've labeled it. And this is 20. The frequency I'm going to care about here is omega equals 10. So I'm going to put 10 in here. And remember, this is omega and radians per second. Be careful with this because engineers actually prefer to use hertz. MATLAB, Multisim, I think, defaults into hertz. MATLAB will default into radians per second. Linear, that's 1. This is 100. This is 1,000. Or a kiloradian per second. Okay, we're going to have a phase graph. We're going to have to do that one too. We're just going to plop this underneath it. 1, 10, 100, and 1,000. These are all drawn. And this is still omega, and this is phi in degrees. Much neater versions of these graphs using rulers and pencils in these slide solutions. So the first factor I want to do is K equals 30. Well, I've got to put that into dB. So 20 log of 30. 20 log of 30. 17. 20 log of 30 is about 36 dB. No, it's 29.5 dB. So it's a little less than 30. Let's put K. Yeah, let's put K. Oh, great. Okay, everybody move to the left side. Blue. Of course. Okay. So this is 29.5 dB. So I will go back and I look at that sheet, and it's telling me for a constant, all I do is draw a straight line at 20 log of K. So that comes out to be something like that. That's a straight line. Okay. My phase shift for that same constant, this is a pole that's going to fall, so we'll call this 0 degrees, is going to be a constant at 0 degrees. Yay, I'm halfway done. I go back to that sheet. I have a pole at omega equals 10. It's a simple pole. This is the wording on it. I'm going to change colors again. At omega equals 10. Orange is fine. Okay. And when I do a pole at omega equals 10, I know the magnitude plot. When I look back at that sheet, it's 0 until I get to, that looks brown. Okay, it's 0 until I get to omega equals 10. And then it falls by 20 dB per decade. So a factor of 10 later, it should be at minus 20. It'll be at minus 40 at 1,000. And this is a straight line. Okay. That is my simple plot. The phase shift for this thing is 0 until I get to 1/10 of a meganaught. So it's going to be constant here. And by the time I get to 10 a meganaught, it's going to be, it will fall, minus 90 degrees. If I don't double check that, I draw them in the wrong direction. And then people get upset with me because I have to rewrite everything. It's easier to redo it on the board than it is in here. So it's going to fall down like that. If I want to find the plot for the entire transfer function, let's see if I can make the color actually change this time. Orange. Okay, it did it. Okay, so all I do is I add these together. Now for the magnitude plot, I have 0 plus 29.5 in this whole region. It's a flat line. So when I add those two graphs together, I'm just going to get a composite that looks like this. After a meganaught, I have a constant at 29.5 dB. And as the frequency changes, I'm adding a sloping line of minus 20. So I'm expecting this to fall by 20 dB per decade. So at 100, it should be around 10 dB. And at 1,000, it should be around minus 10 dB. And then I just draw this in here. There's the magnitude plot of the whole function. I plotted the factors and I added them together. I'm really sorry about the homework. I do the same thing here. This is a little bit simpler because I'm adding 0 to the brown line, and adding 0 to the brown line just becomes the brown line. So we've already done this one. Okay. Okay. Now I'm going to show you a little trick. We take this one here. I have the exact same function. I still have k equals 30. I still have this pole here at omega equals 10. It looks amazingly like the last one, but I've added a 0 at the origin. Uh-oh, I upset somebody. I'll give me a second. Right, if the top function wasn't a constant, okay, so what we're doing here is in this example, Jordan, we're making the top function, instead of being 30, it's going to be 30s. So we're going to add another pole into that. So hopefully this example will answer this question. If I had, what I would do in that case, if I had something else in the numerator, I would just add that third thing into my list of what I have. I would plot 3 things and then add the 3 things together. And we're about ready to do that. Okay. So back to bamboo paper. What I'm going to do is I'm going to take this one and I'm going to add, I got to give this a different color, sorry. Which means I'm going to have to move you guys again. That's fine, you can stay down on the bottom. Let's put something greenish. Okay. So I'm adding in, same thing I had before, a new factor, which is the 0 at the origin. A 0 at the origin is not the same thing as a 0 at omega equals 1. A 0 at the origin is a factor of s. A 0 at omega 1 would be a factor of 1 plus s. They're different, and they're plotted differently. So I go back to my table and I look at the 0 at the origin. And this is the one that's going to be a little bit tricky when we get to lab. My magnitude passes through 0 dB for that ground at omega equals 1, this S factor. And it is a 0, so it's going to float. It's going to go up to plus 20, and it's going to go down. It's got a positive slope of 20 dB per decade. So if this was 0.1, there's really no 0 point on here. It's logarithmic. It has a graph that looks like this. Zeros at the origin, I go back to my chart, have a constant phase shift of plus 90 degrees. If I want to find the composite for adding the 0 in, I can take the old composite and just add the green graph to it. I need another color. This is why I carry around 20 different colors of markers in there. Something blue. Okay. So I'm taking my old composite, which was the orange, and I'm adding it to the green. This is flat here, but now it's like minus. Okay, so I have at no, I'm gonna do this point by point. At 1 radian per second, I have 0 dB plus 29.5 dB. So this is going to be 29.5 dB. At 10 radians per second, I have 20 dB plus 29.5, which is 49.5 dB. I'm somewhere up here. And at 0.1, I have minus 20 plus 30 is around 10. So that takes care of that first region before the change. And this would be 49.5. I really, on your exams, I don't care if it's a little messy, as long as it's labeled. Label it. I prefer neat though. It makes it easier to grade. Now, after I get to omega naught, I have something that's increasing by 20 dB per decade added to something that's decreasing by 20 dB per decade. The slopes cancel out, so this is just going to flatten out at this point. There's my composite graph. Now for my phase shift, I'm going to have to move you guys again. Move to the other side of the room. How do I do that? I don't know. I'll just move you up there for now. Okay, for my phase shift graph, I'm going to add the orange and the green together again. All that does is shift the orange line up by a constant 90 degrees. So it's going to go 0 is going to become plus 90. The final value goes up 90, so the final value would be 0. And then it makes the change in between there. So that's it. You can add one term at a time like that if you want to. Most transfer functions you see in the real world are generally simpler. They only have a couple of poles and zeros. So they're not really hard to plot. there's a trick, and I'm going to go ahead and show it to you because you're probably really frustrated at this point. If I have a really complex function and I don't want to, what slide am I on? Okay, 15. And I don't want to do it by hand. I can do it in MATLAB. You can do this in most tools. What I have to do is, instead of having the factored form, I actually have to multiply this all out. This is the way I know how to do it. Okay. What I do is I create this numerator polynomial, and I just put in the coefficients of the term. So this is 1s cubed, 2s squared, 3s, and 4s to the 0. If I'm missing any terms, if it was, instead of 3s, it was 0s, I would have to put a 0 in there. Otherwise, it misinterprets it. The denominator is s cubed, so I'm going to need 4 terms in that one also. You could do this for squared. It would have 3 terms, etc., 4th, whatever. So this is 1 times 6 plus 6s squared plus 11s plus 6. And then I just type in, it's a built-in function in MATLAB called Bodhi. And you just put in Bodhi, whatever you named your numerator, polynomial, comma, denominator, and you can get these Bodhi plots. And if we look here, MATLAB defaults to radians per second, so you don't have to worry about dividing by 2 pi. Multisim probably defaults to Hertz, and the difference is omega equals 2 pi f. So when you get into lab at some point, you'll go, this Bodhi plot's perfect, but it's off by a factor of about 6.
So they both look the same.
Same shape, but the scale down on the bottom will be different. This is a good way of checking your homework, because you can go through, given the function, do a quick plot of it, and you know what you expect it to look like. And I'm sorry about the homework. Oh. Now, this is probably the worst one you get in here. Okay, we did that one. Did anyone chat? Is anyone? I just want to check the chat. Oh, no new stuff. Okay. So this one, we're not gonna do all of these. A lot of this is looking it up in the table, and the examples are worked out in the slide solutions. I'm gonna tell you about the things you're gonna miss. At this point, if you can do those first 2, you're okay. This one is okay. Well, yeah, I think I did this one. I'll do this one. I've got a K. How much time do I? No, I'm not doing this one. I've got a K. I plot that factor, 20 log of 75. I've got K equals 20 log of 75. I've got a 0, does not begin with S. I've got a 0 at omega equals 100, a simple 0. I have a quadratic pole. It's already put into standard form for me. Its omega is 10. So I have a double pole. At omega equals 10. Plot the 3 factors, add them together. It's practice. And that's the only way you can get there is practice. And one kid a few semesters ago who just really hated this. He was really good mathematically. He just didn't want to put the time in to practice it. So he never got this. He's in the IEEE room, and he probably, his name's Hunter, and he complains about Bodhi plots all the time. Okay. This one's a little bit different, and you will get stuff on the homework and possibly on the exam like this, except on the exam, I never put anything that has an omega naught that is not a multiple of 10. You'll thank me for that later. These 2s are a mess to do. So this one has a K. We got to put it into standard form first before we can say what K is. This is not in standard form. So I got to do a little bit of algebra here. I've got 200, I'm going to switch to S because it's easier to write. I have to factor a 2 out of this term to make it look like 1 plus S over 2. Put it in standard form first. I'm going to have to factor a 10 out of that second term. I'm going to take that 2 and multiply it by 10, and it will be 1 plus S over 10. Put it in standard form first. Now I have to take all the numbers out front. 200 divided by 20 is 10 S over, oh, okay, good. Somebody's barking at me. S over 2, 1 plus S over 10. I'll go back to that. J omega is S, right? Because for this frequency response, we said S was sigma plus J omega. But when we're talking about frequency response, sigma is always 0. So that's why I interchangeably use the S and the J omega. I like writing S better because it's one less character on this scribbly screen. Okay. So now I've got 4 factors. I've got K, 20 log of 10, which should be 20. I've got a 0 at the origin. I've got a simple pole at omega equals 2. And I've got, and there's no way I could draw this on using the screen with non-10 multiples on here. I've got a pole at omega equals 10. I find the Bode plots of each of the 4 factors and I add them together at each frequency and I'm done. But you've got to put it in standard form before you do that. This is the same problem. I've got to put it in standard form. I'm switching to S again. 2, I have to factor a 2 out of the denominator to make this look like 1 plus S over 2. The J omega is an S. And then I'm going to factor a 10 out to put this in standard form, 1 plus S over 10. So this becomes 4 divided by 10 is 0.4. 1 plus S over 2, S, 1 plus S over 10. So I've got 4 factors. I've got a K, 20 log of 0.4. That will be negative. Anything, that doesn't, you can't take the log of a negative number. 20 log of positive 0.4 will be a negative number. I have a 0 at omega equals 2. I have a pole at the origin. Ooh, controls people hate that. At origin. And I have a pole at omega equals 10. So I plot each one of those factors, add them together.
For this example, how do you know you have a pole at the origin?
There's an S in the denominator.
Oh, okay.
Poles and zeros at the origin are marginally stable. And if you have more than one of them, you have an unstable system. It just works out that way.
Where did the 10 go?
The 10? Oh,
Yeah.
I took 4, I took 2 times 2 and divided it by 10, and I got 0.4 in the denominator. So I just multiplied all these 3 terms out, come out to be 0.4. Okay, we got a few more slides to get through. The end slides go fast. It's these that go. Okay. This is a real circuit. It performs the function of a low pass filter. And what a low pass filter does is, okay, let's say I have an audio circuit and the audio is coming from like a radio or a Wi-Fi signal that has a lot of noise, has a lot of signal and in the megahertz region and in the gigahertz region. What I want to do is I want to filter that all out because it can actually get into my audio circuits and get beaten down in frequency, that's a real term, into the audio band and show up as these annoying buzzes. So I want to filter my circuit down so I only hear audio. So what I want here is, I'm not using these component values, but what I want here is to generate a filter that looks like this. It has an omega naught around 20 kilohertz. That will allow audio to pass and freely and filter out. And maybe this has like 20 dB of gain. And by the time I get to the megahertz, it's down to like minus 60 dB. So it's making those things small. You won't get there with the circuit. I should tell you. Okay. Most of the things we do, be grateful for this, most of the things we do in the homework at least, they'll have omega naughts in the range of 10 radians per second, 1 radian per second. You might even see 0.1 radian per second. Back when I was at the old school, one of my students wanted to build a circuit that worked at like 2 hertz or something like that. And I looked at him, I said, what, are you crazy? I go, nobody builds circuits down there. There's semiconductors. There's too much 1/f noise. Just take, that's bad. It just doesn't work. And he goes, no, I really need to have the circuit sensitive at 2 hertz. And I go, what are you doing? Nobody builds circuitry like that. Turns out he was doing some kind of ghost busting thing. So it was entertaining at that point, so I helped him. I just wanted, I just found this all so ridiculous. The guy also used to be a pro bowler, but that's a whole other thing. So we want to build circuits in the real world. We're normally talking kilohertz, megahertz, even power engineers, 60 hertz. We're not, and 60 hertz is 377 radians per second when you multiply it by 2 pi. No one builds circuits at 1 radian per second. It just doesn't happen unless you're a Ghostbuster. So this is, in the real world, this is probably more like microfarads, and this is probably more like kiloohms. But it makes the math easier. Okay. So you can do that with an op-amp. Not only can you, with these op-amp circuits, you can get both gain and filtering in one stage. And we'll talk a lot about that when 490 in the fall, which, by the way, the prerequisite for my 490 in the fall is this class. So we talk a lot about how to build printed circuit boards. We actually do a little printed circuit board layout. We build a lot of analog circuits in there. It's everything you would need to think about as a PCB designer. I've been there, I've done that. This is a high pass filter, and all I've done between the low pass filter and the high pass filter is I've moved this capacitor. So the capacitor's here, and now the capacitor's here. And this has a frequency response, and we'll talk about this more in detail when we get to the 05 slides. But it has a pass things that looks like this. So now you want to filter out the ghost busting stuff. You want to filter out the 1/f noise in your whatchamacallit, in your semiconductors. And so you put this at the low end of the audio, above 60 hertz, so you don't hear the power supply noise. Maybe put this at 100 hertz. And you put that on one end of your audio circuit, and you put the other one at the other end of the audio circuit. Don't cascade them. There's a way to build a bandpass filter that I just put another capacitor here. we'll talk about that. If you like these audios, the audio stuff, and that's the best you're going to get is my 490 in the fall. Nobody around here knows analog but me. All the old analog engineers retired. And analog is still pertinent, even if you're a digital engineer. Never mind. Okay, so this is a real circuit. We looked this up in our cookbook, and this is like cookbook engineering here. There's a lot of that going on. Here's the circuit I'm given, and it tells me that my omega naught is 1 over C3 R6. That is my low frequency pole when I look at the Bode plot. The Bode plot was given to me too. A0 over A1 is the second pole. So the second pole, omega 2, is at 1 over, because that's flipped over, 1 over R5 C4. And all I have to do is pick reasonable values of, and my DC gains R6 over R5. I put these in the kilo ohm range, and I calculate my capacitors, and as long as they're like nanofarads to millifarads, I'm fairly happy. And there's my high frequency gain is dependent upon that. So I pick a couple of these numbers and I play around until I get the frequency response I want on here. We have the skills now to look at that plot and figure out what the transfer function for this thing is. Look at this. We've got a K. And my K is, you take the inverse log of that. My DC gain is R6 over R5. I've got a simple pole because now it's starting to drop by 20 dB per decade at my omega naught. My omega naught's 1 over C3 R6. So I'm putting a simple pole in 1 over S, and my pole is at 1 over C3 R6. I'll tell you why you want to do this in a minute. How do you know the standard form is you're looking for? The standard form's the same all the time. The standard form for poles is 1 over S over omega naught. And it's in that little plot thingy. And the standard pole for the quadratics is in there too. And that never changes. It's always looks like for a 0, it's 1 plus S over omega naught. And for a pole, it's just a denominator. Those never change. The way I figured out what omega naught was is I went back here and it told me what omega naught was, what my low frequency. Oh, that is amazing. That is, I'm gonna have to rewrite that. It's falling. It's a pole. It goes in the denominator, C3R6. And I just copied the value from this, and this was labeled from this. A0 over A1 is this omega 2, what I called omega 2. That is a place where suddenly the gain must be rising because something's canceling out that minus 20, and it must be a plus 20 dB per decade. So that's putting a 0 up here at 1 plus, what was it? S over my omega 2 was 1 over, I'm sorry about this, I'm just excited. R5C4. Why would I want to know what the transfer function looks like? Now I can take that, I can stick it into MATLAB, I can stick it into anything like that. I can do quick stability checks on it to see if it's going to be stable and where it's possibly going to go unstable. And you'll learn all about that in 325. This is just me telling you there's a point to your education. This is not stuff you're going to have to do on the homework yet. I'll show you. I'll point out the one that shows up on homework. Just remember your math skills are learned by practice. I'm sorry about the homework, but doing the practice will really help you kind of solidify this. This seems like the last couple of weeks have been a big jumble of math, and I apologize for that. But what we're going to do next, starting next week for at least one day, is we're going to apply that math to real circuits and start looking at what have we learned? We've learned how to, just wait. I don't want to start today. Yeah, and that's a Dr. Brower quote, and the next one's a quote from me. I'm sorry. It really does mean wise fool. You've really, at this point in your education, you have learned a lot. You haven't learned a lot of applications for what you've learned, but that's what the next 2 years is about. We'll get there. I'm not going to talk about scaling. I don't put it on the homework. I don't put it on the exams, and I'm just tired of talking about it. This is something very real. I've got a series RLC circuit. If I write down the impedance of the loop, and it has a lot of applications. So the ZR of the loop is going to be R plus J omega L. It's in series, so they're just going to add plus, and I'm going to make it minus J over omega C. Okay. Now there's a special condition that people find very desirable. The impedance is purely resistant. So the imaginary part has to go to 0. So I want to say J times omega, I'm going to have to go ahead and factor out the J. J times omega L minus 1 over omega C has to equal 0. J can't equal 0, so we can just divide by J. We got to do that in lab today. Or wasn't a J, it was something else. I could move the -1 over. Omega L equals 1 over omega C. I can multiply both sides equation by omega and divide by L. And I get omega equals the square root of 1 over LC. So whatever the square root of 1 over LC is going to be that omega. Remember from second order circuits, your omega naught was 1 over the square root of LC. If you ever have to guess what the resonant frequency of the circuit is, you just automatically, and sometimes this happens in the lab, it happens all the time. So you just say, well, it's 1 over the square root of LC. No one will think you're an idiot because it always turns out like this. And people think, oh, at least you're thinking, even if you don't know anything else, you can say that. I've saved myself by just having these things on the top of my head. That is this number, this omega naught, this resonant frequency will also, it'll come out to be the same number whether you have a parallel circuit or you have a series circuit. So this is just like a magic thing. It's like V equals IR, C equals I equals C dV dt. If you know like 5 equations, you can argue on the back of an envelope with anybody. Okay. These filters, and we've already talked about low pass filters and high pass filters for audio circuits to put them in there. The ideal low pass filter, and I labeled these today because it was just, I was tired of this, tired of the guessing game. A low pass filter, the ideal filter, which you can't build by the way, has a gain of 1 inside the pass band. And when I get to this omega naught, after that, it has no gain whatsoever. That's ideal, and we can approximate it. The easiest approximation is a simple RC filter low pass circuit. And we'll be dealing with these circuits in the lab when we get there. And you're going to find that this low pass filter, actually, the transfer function looks like this. Low pass. Looks something like K over Poles full. Let's go. I should know this. 1 plus S. We'll go through the math a little bit later, but it has a transfer function that looks like that. The Bodie plot looks like this. It falls at 1 over RC. Am I running out of time? Yes, I am. High pass, I just switch the location of the R's and C's. And this is the ideal high pass. It blocks the Ghostbuster frequencies and it passes the audio frequencies. Now, in between there, let's say I've got a radio channel at 94 megahertz. And there's another radio channel on the dial right next to that. I want to block out that radio channel, the other radio channel, and just zoom in and amplify, make the radio channel I want to listen to bigger. I put in a band pass filter. And it will only pass a very narrow band of frequencies at the radio station that I want to look at. And the band pass, I have to use an RLC. Unless I use an op amp, then I can get rid of the inductor. You'll find I hate inductors. They're big, bulky, expensive, and they break. So all I do is I put the LC in series and I take the output off the resistor. To get a band stop, it filters out some noise that I have, like the radio station transmitter next door. All I do is I swap the position of the LC and R. I take the output off of the LC combination, and I'm almost done. I am done. Knowing about these filter characteristics might help you. We'll talk about that later. Bodie plots in MATLAB. We talked about that. Good thing to put up on your homework to make sure that to check your homework. I will also help you with the Bodie plots, and we are done. Really quickly, let me just call roll. Lane, are you here? I'll check the chat. Lane. Okay, John Hardy. Peter Schoen. Okay, that's it. I'll be in my office. Don't tell Ben. Right. Okay, you leave the power source where it is. You just, to get from a high pass to a low pass, you swap the location of the R and the C. And you take, for a high pass, for a low pass, you take the output off the C. And for the high pass, you take the output off the R. That is the plan, Jordan. 490 fall 21. It's not, it may or may not be on the schedule. Have they put the schedule up on Louis yet for next year? What? Okay. Because they don't tell me anymore, and I find out from the students. And I have to go look at the schedule and say, wait, that's impossible. You have me teaching 2 classes at the same time. Oh, it's on there? It says staff. Okay, if it says my 490 in the fall is called embedded mixed signal systems. That's me. Nobody else here can teach that. Okay. Okay, I'll see you.
I have a question about the pre-electric circuit.
Yeah.
Which always going wrong for the 2-inch.
Okay. The best thing to do is send me an email, because when I'm sitting in front of my computer over here, I can actually go into the grade book and call up the quiz and your answers and figure out what you were doing wrong, and maybe even I can almost look at your answers sometimes and say, oh, you forgot to multiply by 2 pi or whatever it was.
Oh.
Okay, or you left the units off, or?
Yeah. I was like, I don't know. I
Yeah.
don't know if it's the units or whatever.
Yeah, I don't know what it is, but if I can see the two next to each other, I can usually figure out what's going on.
And I have to train my brain to go backwards because I work in hertz.
Yeah.
We were taught hertz too.
Of course,
So-
because nobody in the real world uses radians per
Yeah.
second, except for mathematicians.
Yeah, so I was doing the resonant frequency one and I was like,
Yeah. There's a 2 pi missing.
yeah, I was like, oh, I guess I should put 2 pi on there because I was like, I was in frequency. I was like, oh,
Yeah,
and then it worked. I was like, cool.
yeah,
All right, I'll just email.
okay. I am stopping sharing. I am killing this.